My name is John Magna. I'm a member of the Thermography Working Group for British Institute of Non-Destructive Testing. Category 3, PCN, General Civil and Electrical, and I was formerly an ITC ASNT Level 3 thermographer. I'm a qualified building energy assessor, and I was a board member and technical advisor for the UK Independent Air Tightness Testers Scheme, which became the Elmhurst Air Tightness Scheme. I'm also trained in thermography and air tightness testing for Infrared Training Ltd in the UK. In this presentation, we'll look at possible roles for thermography in building energy performance surveys, basic fault finding through applications in energy upgrades, regulatory compliance and sustainability certification, and finally look at quantitative calculations of heat loss using infrared imaging data. Once we understand the basics of thermography, coupled with application knowledge, building performance issues are easily observable. And as with all technology, training is essential to develop good camera and survey technique. And a good grasp of construction materials and methods, coupled with an understanding of building physics, is needed to interpret infrared building images correctly by qualitative comparison, typically. So these are typical imaging patterns. For successful building energy performance surveys, we need certain environmental conditions. And depending on the nature of the survey, ideally this requirement is for as close to possible steady state heat transfer, and with a stable temperature difference, delta T, of a minimum of 10 degrees Celsius. No solar gain or moisture on the structure and little wind. And for air leakage identification, we need a developed pressure differential across the structure. And once thermally focused, we can determine anomalies qualitatively by comparison and by recognizing typical patterns. So top left image, we can see cold or thermal bridging, missing and or inconsistent insulation and air leakage. Top middle image, we can see externally open convective loops, or as it's now referred to, thermal bypass behind the plasterboard that's been installed on dots and dabs of adhesive. And in this case, this is where external air has entered the void created between the plasterboard and unsealed blockwork, cooling the surface of the plasterboard and exiting externally. In other words, it's not through air leakage. But although it's often combined with small leakage areas at joints and penetrations, this condition will typically not show up with an air permeability test result, but it can give rise to considerable performance issues. Top right, we have an external image of a failed gas seal in a double glazed window unit, identified during a handover survey. Bottom left image, this is a cold roof construction, wall to ceiling junction at the eaves. And the geometric dark blue shapes we can see is the area between the ceiling joists where there's missing insulation. We can also see that there's an area of misplaced insulation, which is not in good contact with the plasterboard. In the bottom middle image, we can see air leakage under and around a skirting board on a knee wall and a dormer roof construction. And this toothed or flared pattern is typical for air leakage. You can also see how the temperature of the radiator return pipe is being cooled by this anomaly. Bottom right image shows a condensation risk in a corner which is at a lower than dew point temperature. Pre and post energy upgrades, well, for domestic and commercial buildings, thermographic survey can be used to establish the building's current performance. And we can highlight anomalies and localized areas of heat loss. Survey report can help inform developers and builders where weaknesses in the thermal envelope exist and assist in directing resources effectively. Typically reporting by exception, in other words, just highlighting anomalies and ensuring that the area is referenced for positive identification in the report. In general, still qualitative, comparative images are all that's required. And then post-upgrade, a further survey is often requested to determine and confirm the effectiveness of the works and possibly act as a baseline for further surveys. Left image here was one of a series of external facades of a sports hall due for renovation. And a survey was requested by a builder that was planning to bid for the energy upgrade works. Right-hand image was taken in the main bedroom of a certified passive house construction. The external top floor, corner to ceiling area was above the cot where a newborn baby was sleeping, which was being impacted by external air from the eaves, moving under some poorly installed attic insulation and causing what's often referred to as wind washing. This caused localized cooling of the surface of the ceiling by 5.9 degrees Celsius, which in turn led to a cooler corner compared to the rest of the bedroom. The house had achieved the required passive house air change figure of better than 0.6 air changes per hour at 50 pascals pressure differential, demonstrating that the anomaly wasn't as a result of through air leakage. Difficult to find without the use of infrared, and this type of heat loss will increase with wind speed and temperature difference. Thermographic building surveys can often help to inform developers where weaknesses in the thermal envelope exist and demonstrate that they've been addressed post any remedial works. Building compliance testing, air permeability tests are now a mandatory requirement to demonstrate compliance with part of building regulations for all new domestic buildings and new commercial buildings over 500 square meters, including extensions with a floor area greater than 25% of the current building. Using thermography in conjunction with a pressure differential, we can readily identify air leakage areas and provide photographic evidence of their location for reference. With the targets for air permeability test results being driven lower than the compliance minimum by the desire to achieve better energy performance criteria, such as nearly zero energy buildings and passive house, thermography can be instrumental in determining where improvements can be made. These images show considerable air leakage around an external door to the sports hall of a new school building. By creating a negative fan pressure and imaging from the inside, it's possible to identify weaknesses in the air barrier. It requires a bit more care with camera settings and ideally the use of a blower door, because often there's no working heating system in operation during a new construction to create a suitable density across the envelope. These thermal images are not seeing the air movement, but effectively seeing the cooling effect of the air as it's been drawn in and forced through the gaps in the structure, which act like venturis. As we know from Newton's law of cooling, this force increases the coefficient of cooling, which leads to increased heat transfer via convection. The images show typical air leakage areas readily found using a blower door in conjunction with infrared. Bottom left, we've got a sloping ceiling to flat ceiling junctions. In the middle, around unsealed attic hatches, and then to the right, under and around skirting boards and around ceiling downlighter fittings in cold roof constructions. We have BREEAM and LED lead. The BREEAM and LEED thermographic surveys can count towards commissioning and handover sustainability credit as a means of demonstrating the continuity of insulation and avoidance of thermal bridging and air leakage paths in the building fabric. This type of survey must be conducted by a qualified professional according to a prescribed methodology and standard. The level of qualification generally required is a minimum of Category 2 certification under the ISO 18436 standard, such as Category 2 PCN or the ABBY Level 4 Building Thermography qualification. Occasionally, survey requirements may request a Category 3 thermographer to conduct the survey or sign off on the report. The thermographer conducts the survey and produces the report, but issuing the credit is the responsibility of a licensed assessor, who should also verify the thermographer's qualification and ensure that the survey complies with relevant applicable standards. Reporting should be complete, detailed, with thermal images and analysis, and with reference to architect's plans and specifications where any anomalies have been identified. And if reportable anomalies are discovered, then a follow-up survey will typically be required to demonstrate that the issue has been rectified before credit can be awarded. And this image taken from a BREEAM survey report shows air leakage due to the lack of sealing to the side of a window. The relevant standard. Since 2023, the relevant ISO standard for the qualitative qualitative detection of thermal irregularities in building envelopes, infrared methods, is the ISO 6781-1 2023. Currently, though, for a BREEAM credit, it's still acceptable to survey using the now superseded EN 13187. Although I have been informed by BRE that this will change in the future and reference to it will be removed. Although both standards are broadly similar in content and methodology, there are some significant differences. And possibly the most impactful is that there is no longer an option for the simplified survey method, which is in the EN 13187. Also, the ISO 6781-1 states, testing for air leakage shall include a means to vary the differential pressure under the two separate conditions of positive and negative pressure, with minimum 10 pascals pressure difference. What this means is that a survey without the installation and use of a blower door to create the required pressure differential would be difficult, if not impossible, to achieve. And this would obviously increase the complexity and cost of a thermographic survey. It'll mean that thermographers will need to develop working relationships with air tightness testing companies or have access to their own fan equipment. It isn't really practical to carry out thermography on a building at the same time as the air permeability test, as the 10 degrees Celsius delta T minimum required for the thermography would typically cause a static pressure issue for the validity of the pressure test. Then we have ISO 50001 energy management. The primary goal of ISO 50001 is to help organizations enhance their energy performance, including in efficiency, use and consumption through a systematic and data-driven approach. So companies that choose to implement ISO 50001 often employ energy managers or assign individuals to manage the energy management systems. And they're responsible for implementing strategies, monitoring energy use, and ensuring that the organization meets its energy targets. As well as identifying energy performance anomalies, it's beneficial for the company to gather quantitative data. And this is where, by using thermography and software analysis, we can come up with figures which can estimate the cost of anomalies found during a survey. So how do we generate quantitative reports using thermography for buildings? ISO 6781-1 states that an application of comparative quantitative thermography would entail two or more similar building surfaces, components or assemblies operating in the same environment under the same conditions, but one is exhibiting a dissimilar surface temperature. This can indicate a potential deteriorating condition. The subsequent quantitative determination of surface temperature difference or differences assists in establishing the severity of the condition. So good thermographic judgment is required to assess if the temperature differentials are to be considered minor or to be considered as critical. Carrying out quantitative assessments of thermal images of areas of interest and comparing them against areas which are considered acceptable can indicate potential savings to be made. So whilst qualitative images can detect deficiencies, quantitative measurements have the capability of determining severity. Calculations of heat loss from building structures can be very complex, and the Chartered Institution of Building Service Engineers, CIBSE, Guide C, provides the following empirical formulas for heat transfer from freely exposed plane surfaces to air, which form the basis of our calculations. So put simply, the values for phi, which is the Greek F for radiative heat exchange, convective heat exchange, are added together to give a value for total heat transfer or flux, which is Q in the equation. Values for radiative heat exchange and convective heat exchange are derived from these formulas. Radiative heat exchange is given by the Stefan-Boltzmann law, where heat exchange in watts per meter squared is found by multiplying the Stefan-Boltzmann constant by the emissivity of the surface, which is then multiplied by the temperature difference of the emitting surface in Kelvin to the power of 4 to the mean radiant temperature in Kelvin to the power of 4. And convective heat exchange, which is given by Newton's law of cooling, where the heat exchange in watts per meter squared is found by multiplying C, the coefficient of convection, by the temperature difference of the surface to that of the bulk air temperature somewhere away from the surface, to the power of the exponent eta, the Greek letter eta, which looks like an N with a tail. And then we derive the specific relevant coefficients of convection C, the exponent eta plus wind speed, by using table values from CIBSE 3.3.4. Next step is to create an Excel spreadsheet template which contains these formulas with the addition of the size of an anomaly in square meters to be able to give total heat loss. By using the area function on infrared images, we can then calculate the difference in heat transfer between acceptable and defective areas of building elements. Developing spreadsheets enables speed and consistency of results and assists in building up more detailed data. And we can, if required, estimate the effective heat loss across an entire wall or across all the walls of a building. We can account for local weather conditions. Many buildings are kept at controlled internal temperatures, and yearly seasonal environmental data is available. So by using internal and external surface temperatures, we can estimate heat transfer through building assemblies, accounting for localized weather conditions, and apply these to the data from our infrared images. Putting these formulas together, we can estimate total heat loss from walls and the roofs of a building. In this instance, the wind speed at the time of the survey was less than 1 meter per second, and data provided in the report was based on this. However, from data supplied by the local meteorological service, it was determined that the average annual wind speed where this building is located is 4 meters per second, which would of course increase the heat loss under such conditions. Therefore, a second set of data was produced to reflect this. And the 3 different stages of the development were imaged. The areas of the anomalies were estimated and combined with the wall and roof area totals to give figures for heat loss per square meter at the time of survey, plus an indication of what the typical heat loss would be at 4 meters per second. And the sample image here shows a section of one wall of a commercial manufacturing plant to demonstrate to a potential client how the calculation of heat loss would be determined. U values are a measure of the rate of heat transfer through a building component, such as a wall, roof, or window, expressed in watts per meter squared per Kelvin, based on thermal conductivities of dry construction materials under steady state heat transfer conditions. And they use default values for surface resistances, which are the boundary layers where convective heat transfer occurs. With a dedicated spreadsheet, we can account for differing conditions of convective heat transfer and estimate U values based on actual surface temperatures at the time of survey. So by combining U value calculations with our heat transfer formulas, we can determine expected surface temperatures using design U values, account for differing conditions of convective heat transfer, and estimate U values based on actual surface temperatures at the time of survey. We can, by using plans and direct measurement, estimate the surface area of floors, walls, windows, doors, roof assemblies. And there's energy performance software available, which will then calculate the theoretical energy consumption of the building based on standard occupancy and design U values. Often in practice, buildings don't perform as expected, and modified values for building assemblies using quantitative data from infrared images can be used to get a better understanding of actual heat transfer. With this knowledge, we can estimate the additional cost of the poorly performing elements and therefore possible savings that can be realized by remedial action. I apologize for the late start. I had issues, software issues, and I apologize if you can hear the storm raging in the background behind me. But thank you for joining me today. I hope this short presentation has gone some way towards demonstrating that building thermography can go beyond basic qualitative fault finding, and that if required, thermal analysis combined with software analysis can be of benefit for energy performance surveys. Thank you again, and now back to Karen.